name is Brendan Gregg, and it's my privilege to talk about BPF and what this is really about. At Netflix, I've been using BPF for observability superpowers to understand what software is doing. Why is software blocking in ways that we couldn't see before in production? Last week, I had a meeting where we're about to roll out flow accounting at Netflix so that we can log whenever machines talk to other machines. And we can use that for capacity planning and security analysis. At Facebook, they have an open source project called Catron for doing intelligent load balancing, and that's based on eBPF. At Cloudflare, they have a BPF solution for doing DDoS mitigation. Cilium is a product by Isovalent, and that's doing container networking, improving performance, and also doing container security. And there's more and more use cases of BPF that are being developed. It's really exciting. For observability, I've described this as a superpower. It's enabling us to use technologies in Linux that we couldn't before, use kprobes and uprobes in production. But that's just one use case. BPF is about more than that. And for the first time, I want to explain what this is really about. For 50 years, we've had one dominant model for an operating system and how you interact with the kernel. There have been other models proposed, especially from academia. There have been proof of concepts, and there's also been products. You may be familiar with unikernels, and you may be familiar with microkernels, and they changed the model. But they have not had popularity. They have not had widespread use. The widespread model that we're using is applications running in user mode, a fixed API of system calls for them to access resources through the kernel. This originated a long time ago in Multics in the 1960s. And it works, although Multics had multiple rings of security. Now we just have user mode. With BPF, we have a new model. There is a new interface to the kernel. It's BPF helpers. The equivalent would be system calls for user mode applications. This allows you to write kernel mode applications that can access resources and run with high performance and efficiency and with guarantees of security. This is different from, say, writing your own kernel software, or writing a kernel loadable module. With those, you do have access to physical resources, but there's no fixed API. You can panic the machine. You can introduce security issues. If you came to me and said, Brendan, I've written this awesome kernel module, can you run it at Netflix? I'd be very hesitant to do that because it introduces a lot of risk. If you say, I've written this awesome BPF program, can you run it at Netflix? That's completely different. I know I can trust its security, and I know it's going to be performant. And so this is enabling new applications that previously would be very difficult to sell to secure environments. Apart from changing that model, it is also changing, it is providing an alternate state model for writing applications. And understanding this will help you understand BPF. Here I've drawn an ideal diagram to show process states or thread or task states. In Linux, technically some of these states are grouped and they're all in the sleep state. I'm on CPU either in user mode or kernel mode, that's my application. And I can be descheduled and put into the runnable state either from an involuntary context switch or a voluntary context switch. I might go and block on resource I/O. With BPF programs, things look quite different. Things are much more simple. BPF programs are event-based. An event fires and your BPF program runs. There's no context switching states here. There's no scheduler. There's no involuntary or voluntary context switches. The BPF program runs to completion. It will access helpers, which allows it to go into kernel mode and access other kernel resources. And there are spin locks, although we haven't really had a need to use them yet much. This model is similar to what other programming languages have embraced, such as Node.js doing non-blocking programming. And that suits BPF. At the moment, those of us writing BPF applications are doing so largely in C and assembly. In the future, I would expect to see new programming languages designed just for BPF, and they'll be similar to non-blocking languages like Node.js, the way the Node.js APIs are designed. Last year, I attended NetConf in Boston. This is a 15-person invite-only exclusive summit for the network engineers to make decisions on what Linux will do in the next year. Alexei Startoyov, who is the creator of extended BPF, talked about what he wanted to do. And at that point, I was using BPF for observability, coming up with custom latency histograms, measuring latency from different places in production. My programs generally fit within the BPF 4 kilobyte instruction limit. Alexei wanted to change that limit to 1 million instructions. Why? Alexei proposed that BPF should be so powerful you can write full applications in BPF. You should be able to write a Rubik's Cube solver in pure BPF. Alexei was really opening the door to making BPF a new model of programming by blowing away the limits that we had imposed from the past. Alexei's changes were accepted, and so this is now in Linux. It's in the Linux that we're all running. A few weeks ago, Alexei gave a talk at Kernel Recipes in Paris and mentioned an astonishing number. Right now at Facebook, on every server, there are 40 active BPF programs on every server in production. At Netflix, and I checked last week, we're currently at 14 active BPF programs in our base AMI image, the new base AMI image, that will be running on every instance, on over 150,000 instances. BPF is not some abstract model in an academic paper. BPF is not someone's proof of concept. BPF is running in production, all across Facebook, all across Netflix, all across Cloudflare. And that means a lot of new things. How do we system administrate BPF? How do we know what programs are running? How do we debug them? And I'll explain that in this keynote. To help you think about it, modern Linux now has kernel mode event-based applications that are secure, BPF-based. And these can work in conjunction with the user mode thread or task-based applications. What BPF is enabling people to do is move functionality from the kernel out of the kernel so that it can be a service can be defined in user space as a BPF program and then loaded. A number of people so far have used the word microkernel. This is giving Linux capabilities that you would otherwise run a microkernel for. A microkernel is a minimum kernel, and my networking stack and my scheduler and other kernel services are user-level programs. Linux now has very similar capabilities, how I can move functionality out of the kernel. That's great as an end user because now you can really customize things. You don't like how TCP does congestion control, write your own version. You don't like how the scheduler is doing something, write a different algorithm, and then you load it up. And this is using a fixed API, as I said, the BPF helpers. Much easier than writing kernel code where you have to integrate with any of the thousands of kernel functions. Stephen Restet is a kernel maintainer who looks after ftrace. Posted this tweet, BPF will replace Linux at kernel recipes. It's been the running joke at all of the recent Linux conferences that they're becoming BPF conferences. Linux Plumbers that just happened had over 20 BPF talks, and the previous one also had over 20 BPF talks. And I understand why. In observability, it solved all these problems I had, and so now I can do all these new performance tools. And that experience is happening for other developers as well in other areas. And that's why BPF is bigger than just my performance tools. It's going to affect all areas of operating systems. So I want to go through BPF Internals to help you understand it. BPF itself is an old technology from 1992. It stands for Berkeley Packet Filter. If you use TCP dump, it will take your filter expression and then turn it into this virtual bytecode that the kernel can then execute on packets. This is to make packet filtering perform. It's actually important because packets can be a high frequent event. I can have millions of packets a second. And if I want to only trace some packets, I need a filter that's quick to run. But really, this is an obscure, arcane technology in Linux that very few people would care about. What was interesting about BPF was that the way it was implemented as a bytecode, BPF is a virtual machine that's in the kernel. In order to make other technologies possible, in the past, people have proposed adding virtual machines to the kernel. And that's a very big undertaking. Alexei Staritoyev realized that BPF was a minimal virtual machine, and it was already in the kernel. And so he extended it so that it had more capabilities. It could call more actions, it could do more things, it could match new modern processors. And with the help of many other people, we now have BPF, which is enabling these new technologies. There's micro-conferences about it. I have a book coming out about BPF performance tools. BPF is now an industry beyond this narrow technology for TCP dump. It enables all sorts of different applications: firewalls, observability, container security. These get compiled and run through a verifier that will reject anything that's not safe. And then the event sources can be from many places: sockets, kernel dynamic tracing, any kernel function, any user space function, trace points. The way we use uprobes, we can also do user, statically defined tracing. Perf events, which has lots of event sources as well. We just began writing BPF programs to be triggered from memory watch points. That's where I can ask the processor to inform me when this particular memory address gets changed. Now imagine being able to write a program that says, when this variable gets changed, run this program and tell me about it. And it's efficient because it's using a hardware level capability and then goes into the kernel and runs the BPF program. I keep saying BPF. For a while, we were calling it extended BPF and abbreviated it as eBPF, but Alexei prefers to call it just BPF because he sees it as an instruction set like x86 and ARM. So he wants it to be 3 letters. BPF nowadays doesn't have much to do with Berkeley packets, or filtering. So we're treating it as a technology name and not an acronym. Some internals. So I mentioned it goes through a verifier. There is a JIT compiler and also an interpreter that will then turn the BPF bytecode into machine code for execution. This turns out to be an important feature. So early last year, the Spectrum meltdown vulnerabilities became public, and that involved changing many layers of the software stack. I think all layers had to change, from the CPU microcode, hypervisor code, runtime code, and compilers, and application level code. There's one type of software that was not affected by Spectrum meltdown, and that was BPF bytecode. BPF bytecode became secure to Spectrum meltdown because we changed the JIT compiler. And so the BPF programs then get compiled slightly different with the workarounds for the security vulnerability and then executed. Now, this is amazing. It means if a security vulnerability becomes known, we patch the JIT compiler, and then all that software immediately recompiles with the security workaround. So it's another use case of why BPF is becoming very important as a part of a solution for writing secure kernel-level software. It's so important that some distros are turning off the interpreter. They're compiling it out. So the interpreter doesn't exist anymore because they don't want anyone, they want all BPF programs to go through the JIT compiler so that it can automatically patch over Spectrum, Meltdown, and other issues. BPF is getting so powerful, people have asked, is it Turing complete? Is it possible to have a BPF program that can run BPF programs, that can compile and execute it? Would be a test. And we've had some serious discussions about this, are we there yet? And the answer is no. And it's no because the verifier rejects unbounded loops. And so there is some things that are not possible. We do have bounded loops in BPF now. I drew this table to help explain how BPF programs fit with user mode programs and kernel mode programs. BPF programs are user-defined. If I need to change the kernel and customize a bit, I can. I don't need to upstream a change and download a new kernel or recompile a kernel. JIT compiled, which I mentioned, is a benefit for security. Whereas kernel, if I have a kernel module or kernel software, it needs to be recompiled. Security is verified, and I have the JIT patching vulnerabilities. The failure mode. With BPF, it fails by giving you an error message. It will reject a program. If you get something wrong in the kernel, if you're lucky, the kernel panics. If you're unlucky, you get silent data corruption, which is really bad. And resource access, it's better than user space. I don't need to either context switch or mode switch, depending on the processor architecture, to access resources. I'm already in kernel mode, and I can access them through restricted helpers. Not quite as good as the kernel, because the kernel has full direct access to anything, but that's a large improvement. As an example use case, BPF observability is where I've been spending my time with BPF. And why it's important is it enables a new class of performance tools that are customized, efficient, and we can run in production. And I can leverage all these other instrumentation sources in Linux and come up with new tools based on it. I have a new book coming out. Hopefully it will be in physical form next month. It's already on Safari, so people are reading it right now on Safari as a draft. BPF Performance Tools, to be published by Addison Wesley. And I've decorated a kernel diagram showing the all the different BPF tools that we now have for observing what's going on and getting to the bottom of all sorts of issues. In red are the new tools I developed just for the book. We've been working with Canonical all along with BPF to make sure the Ubuntu supports it. And using BPF for observability is simply a matter of apt install BCC for the BPF compiler collection that contains many performance tools. And the newer one is bpftrace, which is more suited for one-liners and short programs. And that's also available. And these are also available as snaps. I should also mention that these two programs, BCC and bpftrace, these are default installs at Netflix. This is written at base AMI. As the first example, a very popular tool I wrote is called TCP-life. And it began with a tweet from Julia Evans who asked, I wish I had a command line tool that would tell me, for this port, give me some TCP statistics. And I saw that this could be done efficiently using BPF. There's TCP-life. It's telling me who connected to who, but it's also giving me information such as the process ID and the program name, the number of bytes transferred, and the duration of the connection. BPF enabled me to write this efficiently. Instead of using TCP dump to filter or capture every packet and look for sins and look for closing connections, with BPF, I instrumented just when the kernel changes the state of a connection. And so just when TCP does, or the kernel function TCP set state, and we added a trace point for this. That's much more efficient because I might do 10,000 packets for a connection, but I only change state several times. And overhead is proportional to the rate of events. So just by instrumenting the set state, this program is, the performance overhead should be negligible to run in production. Our Netflix network engineering team have enhanced this program, and they're going to be running it 24/7 across the fleet so that they can capture all of this flow information for later analysis. And other people are doing this already as well. In fact, these BCC tools behave like normal Linux tools. So you don't really need to know that much about BPF. It has a usage message, a man page. I can say, just show me connections to this local port. As another example of a BCC tool, biolatency. And these are all open source, and BCC is open source. It's all on it's a GitHub account called IOVisor from the Linux Foundation. Biolatency records disk I/O latency and shows it as a histogram. But it does this efficiently. It calculates, that count column is calculated and summarized in kernel space. And when we wake up to print out the ASCII distribution every second, we just copy that array of numbers once to user space. Prior to BPF, my previous solutions to this involved dumping every disk I/O to user space and then post-processing it. And doing that on our Cassandra clusters, which can be doing 10 to 50,000 disk I/O per second, the overhead adds up. So this made this a production-safe tool, overhead negligible. And also doing 1-second histograms of disk latency can be visualized as a latency heat map, something I created many years ago. And so you can look at variations in latency over time. I can identify multimodal distributions and outliers. And so we're using that at Netflix as well. As an example of bpftrace, that's the other BPF observability software. For many years, I keep saying, one of these days, I'm going to write a program that tells us if file system readahead is working or not. There's all these algorithms inside Linux and inside your applications as well that you assume work. How does libc do allocation and caching of allocated pages? Does that work? Or are they broken? Is it broken? Is there some optimizations we could be implementing? These assumptions are throughout the kernel. And And here's one of them. It was readahead. Is readahead actually working? That's when the file system detects you're reading a sequential workload and then will prefetch the next pages to warm up the file system cache before the application needs it. But if it's tuned incorrectly, it's pulling in pages that the application doesn't need, and it pollutes the page cache, decreasing performance. Or if it's not reading quick enough, you could increase it to improve performance. So, had this need for a while, finally knocked out the tool. It tells me over a given interval how many read-ahead pages were unused, and the age between reading in a page and when it was used. Most of the time we used a page within 32 milliseconds. So it looks like read-ahead is being effective. The application wants it. So I'd look at this and consider increasing the read-ahead tunables. If it instead showed that the age of the read-ahead pages was hours or days, that would tell me something else. It would tell me it's doing read-ahead too aggressively, and it's loading all these pages into memory that the application didn't actually need for hours. And so the database engineering team are particularly interested in this and similar tools to understand what happens to the database disk I/O and how the page cache gets used. So far, this looks like a BCC tool. I can run it. It gives me some text output. What makes BPF-trace different is it has a high-level language, BPF-trace, and that program can actually fit on a slide. BCC is great for doing these very custom tools, but BPF-trace is great for these short tools or one-liners. So I'm instrumenting kernel functions, do page cache read ahead, I'm setting some variables, I'm doing the calculations, and then I print it out. Fits on one slide. There are some challenges, and off-CPU flame graphs is what we really want to be doing more of, and BPF allows us to do it. But libc by default has no frame pointer, so stack traces get broken when you trace it through libc. And also JIT function tracing is also a challenge we're working on. Those tools are great, but at Netflix we actually get most of our wins from CPU flame graphs, like these. Hands up if you're using flame graphs. Okay, so like a third of the people. BPF is changing that as well, because it's allowing flame graphs, the stack traces, to be summarized in kernel context, and then only the summary passed out to user space. So it eliminates these CPU-consuming steps. Now that BPF is being used in production everywhere, how do we look at BPF programs? For normal programs, we have PS, top, PMAP, and so on. So we're now developing new tools. This shows that this is a real thing, that a real software type that we're all using and we need to debug. It's in production. We have BPF tool. It's in the Linux source. In a way, its version of a process listing. This is listing the BPF programs running on a Netflix server. And it shows, if it can, what events it's instrumenting. It can also do instruction listings of programs. There's the assembly for something that was running. At Linux Plumbers Conference this year, Arnaldo Mello talked about, well, actually gave demonstrations of perf top can now show BPF programs and give you context. So perf top does CPU cycle sampling by default, and that's now capable of doing BPF introspection. So if BPF is consuming a lot of CPU cycles, we can see it this way. And at the Linux Storage and File System Summit earlier this year, David S. Miller, the networking maintainer, talked about we should be able to take a core dump of a BPF program that contains all state. We should be able to single step through a BPF program. And so these are the challenges we're working on now. And this is a consequence of something that's really being used in production. We need debugging tools. In the future, and I've already talked about much of this, there's many use cases for BPF, and there's many we're only just discovering. Alexei increasing the instruction limit to 1 million instructions, which he said I shouldn't say that number because if people run into it, he'll increase it again, is only the beginning. And so that's that's fairly recent, and it's enabling people to write much more complicated BPF applications than they have before. And so we will see device drivers. Greg Cora-Hartman actually talked about USB on BPF at kernel recipes. Monitoring agents, intrusion detection systems, TCP congestion controls, many new technologies. If I was to give you 2 takeaways, it would be that BPF is a new software type, and try out BCC and bpftrace, which are packaged for Ubuntu. Thank you very much.